Hello and welcome to this edition of GEMS tutorials. This is a two-part tutorial. In this tutorial, we will look at defining a simple beam foundation, soil properties, and applying concentrated loads to it. The second part, we will improve this and look at applying moments and uniformly distributed loads. We will be using GEMS beam foundation software for this. This is part of the larger GEMS foundation analysis suite. GEMS Foundation Analysis Suite brings you feature-rich, easy-to-use CAD software for foundation design and analysis. The suite uses finite element modeling techniques for design and analysis of shallow and deep foundations. The software is available for a 30-day trial download from our website. One can also try the online cloud version for 30 days from our website using a browser. For details on the software, visit our website at https://www.gemsoftware.org. The download links and the cloud links are given in the slide below. So let me go over the problem that we will look at solving in this case. So we have a 3-story building resting on 6 columns, and which on top rests on 2 beam foundations. We are looking at a beam foundation dimension of 10 meters by 1.5 meters wide and 0.5 meter deep. It's about 1 meter below the ground. The advantage of using combined footing is to increase the total bearing capacity and reduce differential settlement. It is common practice to carry out a plate load test in the site to determine the subgrade modulus. It is also possible to obtain the elastic modulus using a Poisson ratio. In this case, we shall use an elastic modulus of 45,000 kPa and calculate the corresponding value of the subgrade modulus using the often used basic formula. We have estimated the building load to be about 6,000 kilonewton. Now, structural analysis gives the load distribution as shown in the figure below. The load is distributed equally amongst the 2 beam foundations, each carrying 3,000 kilonewtons. Now, the 3 columns on each beam, the outer columns carry 750 kilonewton, while the central column carries 1,500 kilonewton. We will now look at defining the problem using our software, applying the loads, and then analyze it using discrete spring bed method and elastic half space method. Open the GEMS beam foundation analysis software on the screen. The software has 4 tiles on the left side: project properties, where you will define the project; input parameters, to define the input parameters, beam dimensions, etc. And then the 2 analysis models: discrete spring bed and elastic half space, where we will see the results. So let's start with the project title. Let's see, building foundation, 3 floors, analysis of building foundation using concentrated loads. See Example1a, GEMS. Analysis model, we have defined 2 analysis model: discrete spring bed and elastic half space. We'll use both the methods. You can use either or methods. We have one loading scenario in this case where we will evaluate the loads using concentrated loads. From the units perspective, we will use SI units, since all our loads, etc., and beam dimensions are in meters and kilonewtons. Next, we will look at entering the input parameters. The input parameters has 4 tabs: beam dimension, beam properties, soil properties, and load cases. So let's start with this. Beam length 10 meters. 10. M is not required. Number of elements, it's a guiding number used for finite element calculations. Gives you the granularity of the calculation. Let's leave it at default as 20. For beams, larger beams or longer beams, you can look at increasing it all the way to 50. The beam is 1.5 meters wide, and it extends all through the length of the beam. And the depth of the beam is half a meter, and again extends to the length of the beam. One can define beams of different segments with different breadths and different depths. So, but since our beam is a uniform beam, uh, just one entry is enough. The diagram below shows the plan and the elevation of the beam. In this case, it's 1.5 meters by 10 meters and half a meter deep. Beam properties. Beam properties, we define the beam material. Let's say we picked M30 concrete with an elastic modulus of 3.3 into 10 raised to 7 kilonewton per meter square and a unit weight of 24 kilonewton per meter cube. Fluctual rigidity table, we will leave it blank. We will let the program auto-calculate the fluctual rigidities. It is possible to also have user-defined fluctual rigidities in case you have beams which are not purely rectangular. Prescribed restraints, we'll have a separate video describing the use of this. This defines how the beam gets restrained. Since it's a free beam, there are nothing to be specified in this. Soil properties. So from our investigation, we saw the soil to be having an elastic modulus of 45,000 kilonewton per meter square and a Poisson ratio of 0.2. Subgrade modulus, we calculated it as 18,975, and the subgrade modulus extends to the end of the beam. This can also be determined from plate load tests and entered here. If you have along the length of the beam different types of soil, you can also enter different subgrade modulus. For us, it's just a single entry. Load cases, so we have a 3 concentrated load. Let's assume we also include the self-weight of the beam for our analysis. Now, we enter the concentrated load in the concentrated load table. We'll set it as 3 load cases here. The first load case, the outer left, let's say it is at half a meter with a load of 750 kilonewton. The second load is applied at the center of the beam with a load of 1500 kilonewton, and the final load is applied at 9.5 kilometers and a load of 750 kilonewton. We don't have any moments in our problem, so we leave the moment section as all zeros. We don't have any uniformly distributed loads either, so we don't need to populate this table. The loading diagram is displayed below, shows a beam, 10-meter beam that we have with 3 concentrated loads applied, 750 kilonewton, 1500 kilonewton, and 750 kilonewton. We are done with giving our properties. Let's look at our analysis. Before we start, it is probably a good idea to clear all our outputs so that the output tables are all empty, and also validate our inputs. It shows inputs are valid. If there are any errors in inputs, it will give you an error message detailing what needs to be corrected. So let's analyze or compute. And voila, done. We have execution complete for discrete spring bed and elastic half. Quite quick. Let's quickly just review the results. So let's start with discrete spring bed model. There are 2 panes in it. The left side pane gives the tabular representation of the results, and the right side pane gives you the graphical representation. We have 1 load case, so we will review load case 1. We can see the overall displacement of the beam, slightly more displaced on the edges than with the center. The central displacement is about 10.81 millimeters, while the edge displacement is about 13.76 millimeters, fairly within range. The next one gives you the slope, which is delta y by delta x. The shear diagrams shows the 3 shear where the three loads are applied, and the bending moment diagram for our beam, pressure diagram, and the soil reaction diagram. This is also tabulated on the left side. The first table shows distance with displacement and slope. The second table gives you the shear and the bending moment, and the third table gives you the pressure and the soil reaction. Now let us see our elastic half space results. Again, same layout, left side table, tabular results, and the right side graphs. Here, the elastic half space results gives a central displacement of about 15 millimeters and an edge displacement of 12.5. We may also note that the average settlement in both cases is sensibly similar. Next comes the slope, shear, bending moment, and the pressure soil reactions. Now, the difference in the shear force and bending moment diagrams between the two, let's just see. There's some numerical differences if you look at the two, is due to the difference in the contact pressure distribution diagrams. Right, this is the discrete spring bed, and here in the elastic half space you see the differences. And the elastic half space model accounts for the edge pressure better, and so you see the elastic half space having a kink in the edges. The behavior of the actual soil is somewhere between the results obtained by discrete spring bed and elastic half space model. This is due to the full continuity of the soil medium assumed in the elastic half space model and completely discrete springs in the discrete spring bed model. In our view, it's important and it's preferable to carry out both the analysis and choose the design parameters appropriately. To recap what we have done today, we started a new project for foundation analysis, defined beam dimensions and properties, defined soil properties, added load transfer to the foundation via the columns using concentrated load, and analyzed the foundation design using discrete spring bed and elastic half space model.